All right, folks, this is day 2 of confidence intervals for proportions, and I'm going to cover kind of a lot today, but I think we can get through it pretty quickly, especially since you will be doing pause and I'm not going to be doing any writing. So we'll just start out. This was page 1, and don't try to write all this. I'm just going to kind of bounce around within a slide and summarize. So what we learned yesterday was, empirical rule, 95% confidence, that's plus or minus 2 standard errors to either side of a sample estimate, which is right here in red. All right, so sample estimate plus or minus 2 comes from the 95% confidence times the standard error of p hat. All right, now this, after this plus minus sign, the 2 standard error of p hat is the margin of error, extending 2 standard errors to the right and 2 standard errors to the left of your sample estimate. So in general, your confidence intervals have the form of sample estimate, be they p hat values or x bar or whatever you're making a confidence interval out of, plus or minus margin of error. And margin of error is sort of a fluid thing depending on how confident you want to be. So if we go, say, to 99% confident, then we're going to make less mistakes in our estimation. Of course, remember, we lose precision, but we're going to stretch out further and capture more values. So if we're right on the edge of, say, trapping the true parameter p with a 95% confidence level, if we extend it to 99, then we're sure to capture it. All right. So the larger our margin of error needs to be, the wider the interval. And that's the more error we're willing to accept in our estimation. All right, so let's get this going. All right, here's the happy guy who is demonstrating plus or minus 3 standard errors. That's your 99.7% confidence, and that's just making things wider. We would never really have a confidence level like this, but we'd have ones that would be close. All right, so yeah, so we're kind of balancing this tension, here's this word tension, between being certain or being successful in estimation and precision. All right, so the issue is, the more confident we are, the wider the net we cast, the more error we're willing to accept, and we're going to wind up being less precise. So there's this balance between certainty and precision. And the good news is that the typical values that we use for a confidence level, 90, 95, and 99%, 98%, and any of those values are going to give us a pretty good balance between certainty and precision. I think in a lot of cases, people pretty much agree on 95% as a kind of a sweet spot. So this is kind of just saying the same thing. As far as what level of confidence you want, you're going to be picking it. So it's sort of arbitrary. There are no hard and fast rules. If you want more precision, go lower. If you want to be more accurate, well, I don't know if accurate is the right word, but if you want to be more successful in your estimation of your parameter, then a bigger value is in order. Okay, but what about other levels of confidence? All right, 95% is great because the empirical rule says plus or minus 2 standard errors from the sample estimate, but maybe we want something different. All right, the weird thing is if you use the empirical rule, 2 is a good measure for the number of standard errors, but it's actually not perfectly precise. In a normal curve, 95% confidence is actually 1.96 standard deviations to either side of your estimate. It's really not 2. All right. Now this little deviation of 0.04 in the number of standard errors to either side is really not that important. I mean, the whole process has its flaws, and it's estimation, approximation. So what difference is it going to make much between 1.96 and 2? So, excuse me, if you're doing a 95% confidence level, you can put 2 in there, you can put 1.96. Either way, this position is your critical value, and we will denote it with a Z star. That's what we call it. So if I say, what's the Z star for this? You'll know it's that number that denotes how many standard deviations you're using in your margin of error, right? So we can actually figure out any value of Z star for any confidence level, all right? So here's some options. This is going to be something I'm going to come back to, so just stand by with that. All right, some common ones. For a 90% confidence level, it's actually 1.645 standard deviations to either side of your sample estimate. And 95% is 1.96 standard errors to either side, which we just saw. 98 is 2.326 standard errors to either side. And 99 is 2.576. Now, how do I know that? It's because I have done this enough times that the more common ones just fall into your memory. So while I wouldn't ask you to memorize these, you will be able to know them just for having used them so often. So here is one way to find Z tables. Now, I didn't give you one in the packet. That was an oversight, but there is one that's posted up on Canvas in reprints. Print it out. You can just do a Google search on Z star, T star critical values, and up pops a whole number of different options for you, but pretty much the one I posted is a pretty good one. Now, T star is not what we're using now. When we get to means, we'll start using T star. So most of your table are T star values. In fact, this table's been cut out a little bit just so that it can fit into the screen. Yours will be a lot longer. Here's what you do. Go down, and these are some confidence levels that are provided. They're certainly not all of them, but there's some ones that are used pretty much all the time. So 90%, 95%, 99%, 99.9, 99.5, those show up quite a lot, right? And you don't really have everything. So there's no 97% confidence listed, for example. So, well, I'm going to show you what to do with that. Okay, so the way that you read it is if you're doing a confidence interval that's 90%, go to 90% and read straight up, and that's your Z star number, 1.645, and the number immediately above the confidence level. So 95%, there's your 1.96, 99%, 2.576, remember I told you that one? So you can use this on any test or quiz. I, however, don't use them. I've got the more normal or the most frequently occurring ones in my head, and I'm going to show you how you go about figuring out these things when you don't have values that are on this table. All right, so here it goes. I'm going to go ahead and pause this because I need to draw something out. So stand by. All right, I'm back, and so this was a little demonstration I did in class to show you how you can calculate these things sort of by hand. All right. There is an algebraic approach. It'll be in the PowerPoint in a minute, but I think just seeing this step by step will make it pretty clear. All right. So we're just kind of mimicking here a 90% confidence interval, right? And keep in mind that a 90% confidence interval, or any confidence interval, takes your sample estimate as kind of the middle, the exact center of your distribution, like this, normal curve, and it works its way out to either side. So it's really the central 90% of the curve that you're talking about. It's not from the left to the right, it's not from the right to the left, it's from the center on out, all right? So since this is a density curve and this is 90%, that's going to leave 10% left over for the two red tails. Now, as badly as I drew them, those tails ought to be equal area because normal curves are symmetric. So that means that if 0.10 is left over, that will leave you with 0.05 here and it leaves you with 0.05 here. Okay? So we need the z value here. How about we just do inverse norm 0.05. And if you do that on your calculator, remember in a scratch pad, it's menu 55, and I think it's the third choice, you're going to get negative 1.6444, whatever, 45. Let's go with that. All right. That's going to be the same number as over here, positive 1.645, right? Because it's a symmetry and it's the exact number of standard deviations from the middle. Okay. So yeah, the only issue is if you do this, you might get that negative sign, and no z star values are negative. So in order to get rid of that from the start, you can put your negative sign right here. That will go positive, and then that becomes this value right here. Okay? So let me just show you. That's actually one you can look up. So I'm just going to get rid of all of this stuff. Just bear with me as it goes away a little piece at a time. All right, so, and I need this to go. Let's see. Okay, so let's pick something that is not on that z star t star table. Okay, let's do 0.97. So we're talking about a 97% confidence interval. All right, your z star value is not there, but we'll figure it out same way we just did with the 0.9. All right, so again, it's the central 97% of your normal curve, leaving 0.03 or 3% left over, half of which goes here. So this will be 0.015. Oh, that's interesting. And this one here is 0.015. Right, go away. And we just do the same thing. This is inverse norm, 0.015. And we'll just take the opposite of that, and that'll give you your z star, which is, I believe, 0.170. And there you go. You just do that in your calculator. So let's go ahead and go back to the PowerPoint and look over those notes and about that little section I just showed you. All right, so we're from the current, and okay, so from the calculator, let's just say you're looking up 97.5 confidence interval. That's a little weird, but let's say that's what we need. All right, take your, that's your confidence level, express it as a decimal, 0.9750, subtract it from 1. That leaves what's left over in both tails. Divide by 2, that's what's left over in a single tail. Inverse norm that, you'll get the left side, take the opposite, that'll give you the right side, and that's your z star number. So I never remember this, so I actually draw a quick sketch, you know, to make it look sort of like that, and it maybe takes me 30 seconds to figure it out. But yeah, if you're good and you can remember this formula, by all means use it. Okay? Okay, so this is, I believe, in your packet on page 5. So I've got that on standby here, so let's pull it up. And where'd it go? Here it is. All right, so this one is going to be a little bit strange. It's about people having bicycle accidents, the ones that are fatal, and drinking. So in the US, about 900 people die in bicycle accidents each year. And we've got a study examining the records of 1,711 bicyclists who were fatally injured in bicycle accidents for those 5 years listed and were tested for alcohol. Of these, 542 tested positive for alcohol, right? And so we're supposed to find a 90% confidence interval for P, the true proportion of alcohol-related bicycle fatalities. Okay. So P hat is down here. I wrote it down in number 3. 542 out of 1711 is 0.3168. So that's our sample estimate. And the first thing we need to do is define the parameter. So P is the true proportion of alcohol-related bicycle fatalities in the United States. All right, so every time that we go over a section, I'm going to just pause for a few seconds, meaning you're pausing to write. So pause. Okay, so the next thing to do is to list your assumptions. Now, when I read this up here, I don't see anywhere where they're talking about random selection. They're just examining some records. I don't know where they're coming from. I don't know how they were picked. It seems to me that this may not be random. So I wrote SRS is not given. Okay, now for the population being at least 10 times the sample size, I said that it was, or that I thought maybe there was enough haziness in the problem that we could get by with saying it. When I did that second period, a couple of kids revolted and said, nah, I don't know about that. Because if you take 900 people who die per year times, 87, 88, 89, 90, 91 is 5 years, that is 4,500 people, okay? Your sample is 1,711. 5 times 900 is 4,500. Yeah, I don't know that your population is 10 times your sample size, all right? So you can write here that you're not happy with that. Just say the population may not be at least 10 times the sample size. The point is that we have at least one violation of assumptions. Maybe there's two. Now, if you want to go and check the normality of your sampling distribution, remember it's n times p hat, n times 1 minus p hat. Now, I didn't write out exactly what the values were that go in there, but I did write out the products. They're both over 10. Now, don't just write n times p hat is greater than or equal to 10 and n times 1 minus p hat is greater than or equal to 10, because that doesn't really show that you checked them. So at least give the products. So here they are. Both exceed 10, so normality of your sampling distribution is approximated. So at least we have one of the three. Okay? So go ahead and pause and copy. All right, here's number 3. Now name this. Definitely name this, because we're going to actually end up doing this straight on the calculator. So this is a result for a 1 proportion z interval, and it's a 90%, so it's a C90 equals your p hat 0.3168, remember from over here, plus or minus, and you can look up 90%, remember, or figure it out the way I showed you, 1.645 times your standard error. All right, that's going to be p hat 0.3168 times 1 minus p hat 0.6832 divided by n, which is 1,711. And all of this gives you a margin of error of plus or minus 0.0185, plus, minus to your sample estimate. So when you do the final math, you get 0.2983 up to 0.3353. Okay? So I'll let you pause and write that. Okay, so now that you're back, I'm going to show you how to do this on your calculator. This is on an Nspire. You can do it also on a TI-84. So I'm going to go to a scratch pad, all right? And so hit A. And you want to go into your stats menu. So menu, choice 6 is statistics. And then another choice 6 is confidence intervals. And a lot of them pop up. Now don't do that one that's highlighted in number 1, Z interval. You want a 1 proportion Z interval. Okay? Those two are not the same. So pick the one that's choice 5. And it's really pretty easy. All right, there were 542 deaths that were alcohol related. That's out of 1,711. Now don't forget to change your confidence level. It defaults to 0.95. We want 0.90. Okay? Hit OK. All right, here is your lower bound, 0.2879. Your upper bound was 0.3246. I believe those were the numbers we got, or at least close. Let's just see if we're close. All right, something seems to be amiss. Let me just double check what my numbers were. Oh, it's 4-2. My bad. So let's go back and fix that. All right, it always helps to double check what you're doing. All right, so confidence intervals. All right, so 542, that'll be a little bit better, and 1,711, and 95, so 0.90, and okay. All right, that's better. These are exactly the same as what I got just by doing it by hand. So I need you to use the top two numbers here for your confidence level and record the p hat value. Just say p hat equals this. Of course, you have your margin of error. That's what you do, plus or minus your p hat value. But anyway, those three things ought to do it, so long as you say what your confidence level is. All right? So let's see here. Hang on just a second. I want to show the 84 people. Okay, so for you guys with a TI-84, you just go to Stats and over to Tests, and you got to kind of scroll down a little bit to find it. It's a 1 prop Z interval. There it is. So hit Enter. X is the number of successes, 542, and N is the number of trials, 1,711. Make sure that you change your confidence level, 0.90. And just go down to calculate. All right, there is your confidence interval, and there's your p hat number. Just write that out and you're good to go. All right, so let's go ahead. I'm going to close that out and get back to what I was talking about here. So, all right, so everything is now complete except to interpret. So we're 90% confident that the true proportion of alcohol-related fatalities in the United States involving bicyclists falls in the interval from 0.2983 to 0.3353. I should not have that parenthesis there, just ignore it. However, since the sample might not be random and the population may be too small, possibly, if you believe that, our results may be invalid. Okay, so jot that down. All right, here is the usual thing. It's not really part of the question. It's just a general question about 90% confidence. What does it really mean? And I'm going to piggyback on what I wrote yesterday. So this result is based on a method which successfully estimates the true proportion of fatalities from 90% of all samples of this size. Even if you just say that it estimates the true population proportion from 90% of all samples of this size, you can leave out the context because they're really not asking you about the question. They're asking you about what does 90% confidence mean in the context of any question that might be referring to it. All right. So all AP exams ask a question like this, and the trouble is that in many cases it'll be multiple choice, and 3 of the 5 question answer choices will actually look right. So it's a tough question. A lot of kids miss it. Another thing that shows up on the AP exam is there good evidence that alcohol causes fatal bicycle accidents? And it was amazing how few people remembered how to answer this. Well, causation in a situation like this is a function of whether or not you're conducting an experiment, which means you're imposing some kind of treatment. There is no imposition of a treatment here. Remember, a study is examining records. That's just recording what's already there. So it's an observational study. So therefore, no causation between alcohol use and bicycle fatalities can be inferred. All right, so don't forget your context and list the reason why, you answer it, list why not, and keep your context going. All right, so I believe that this was pretty much most of it. I think there were 2 there were 2 slides left. All right, so here was one of the last 2 slides. And what I talked to the kids about was this is the portion of your confidence interval formula that is the margin of error. And if you look at it, if you're looking at what you can do to affect or control your margin of error, well, your sample estimate is whatever you get. So that's fixed. Z star is just a value that you decide upon based on how you're going to balance precision with success and prediction, right? So that's sort of fixed too. But what you might have control over is sample size. So picture this fraction under the radical. If your sample size n increases and gets bigger and bigger, doesn't that make your fraction smaller? Then the root of it is smaller, and you multiply it by z star, and that becomes smaller than it might be if n hadn't grown that large. Okay? So if you pick a higher sample size, you're going to get a smaller margin of error. And a smaller margin of error means that you will have a little bit more precision, right? Because aren't larger samples more accurate? Didn't we learn that? So there it is mathematically supporting that notion. Bigger sample size, smaller margin of error, more precision. All right? So that's interesting. And here, always check your conditions for any sort of confidence interval or any kind of inference. Because if you don't on an AP test, they won't give you credit, or certainly not near as much as if you check them. Also, when you get through and get a result, make sure that you interpret it, whether it be a confidence interval or a test of significance, because if you just throw numbers out at people without any communication or explanation, that's not really good practice, and the AP people will surely dock you for that too.